high Q filter. I just have a filter of maybe a few kilohertz bandwidth corresponding to the carrier of something. I still effectively have a filter that is in kilohertz range. So reciprocal heterodyning allows you to use lower Q filters to get narrow bandwidth electronics. Okay, but what is something that comes with narrower and narrower bandwidth electronics?
Longer time constant.
Longer time constant. Okay, so if you want to measure something that has kilohertz bandwidth, you have to measure with a longer duty cycle. You have to measure for a longer time, because the time harmonic signal is only clearly defined the longer you make the time window. So if you measure a kilohertz signal with a short time window, it's not truly a time harmonic signal. Okay. So one way to increase the purity of a time harmonic signal is to measure it for a longer and longer time. At least the time constant that you measure must be much larger than the number of cycles you have. Okay. So the narrower the bandwidth, the longer you have to measure the signal with for a longer. So that slows down the system. So the barrier to narrow bandwidth is actually the measurement time. Okay. It's like a Heisenberg uncertainty principle, right? The narrower the bandwidth, the longer you have to measure the time in order to get the bandwidth. Okay. So if you want to design very, very narrow band filter, you have to have a very long time constant. And you probably don't want to wait that long in the MRI machine when they take your image, right? Another thing is what? What prevents you from measuring with a very long time constant? What is the other thing that you have to be careful about in the electronic system that allows you to measure with a longer and longer time constant?
Is it the power consumption?
Not the power consumption, the stability of the oscillator. That means that you have to have an oscillator that's highly stable, that is stable for many, many duty cycles. It's actually very difficult to make oscillators that are stable. Okay, so usually you have phase drift. The oscillator will oscillate at this frequency that you prescribe it to be, and then you will have phase drift, and then it will actually drift around. So the real world is not like the world in the lecture hall, right? E to the I omega t, we just write it down, assuming that things will remain e to the I omega t forever. But the real world, you want to get something that goes like e to the I omega t or minus I omega t, it's not there. A pure time harmonic signal is actually quite difficult to generate. You generate with a local oscillator. A local oscillator will drift in frequency and phase. Okay, so you have to grapple with those things. So that is another barrier to getting very narrow band filtering effect. Time constant and the stability of the oscillator. So any question, any more questions you have on MRI? Okay.
When you said narrow bandwidth, you mean low bandwidth?
Narrow band. Narrow band means you try to measure only a small segment of this frequency, right? If you tilt, if you have a gradient field, okay, this might be center frequency of about 42 megahertz. Because of the gradient field, you will get signals coming from above and below 42 megahertz due to this thing, right? If Z is 0, if this field is not there, then you only have 42 megahertz at 1 Tesla, but then you get a broadband response. In order to actually determine where the slice is coming from, you will have to do narrowband filtering. try to distinguish this as much as possible. Okay, with narrowband filtering techniques. And then you can decide where the signal is coming from, which slice it is coming from in position. And then connect that to the spatial slice is coming from, and then connect that to the slice projection theorem, gradon transform, and so on, and do the signal processing. And then you can get a very high MRI image. So it's not low. What was the question again? Is narrow band is not the same as low band?
I don't know. I mean, usually in my head, I think if it's low frequency, it takes a long time to measure. But now we're talking narrow.
Narrow band. Okay, narrow band filtering. The electronic system is actually not designed at 42 megahertz. You look at most of the radio systems, you have something at 42. Then you heterodyne this down to kilohertz. And in kilohertz, it might be working with very low frequencies. You can design filters that are not very high Q. And effectively, it gives you kilohertz bandwidth at this frequency because of the mixing down that you have. Okay. So the electronics are low frequencies, but actually you're actually doing a very narrow band filtering for the RF signals that are coming in at this frequencies. Okay.
So is the time due to the fact that it's narrow, or due to the fact that it's low frequency?
Because you want a narrow bandwidth, you would want to step this down to kilohertz range, or in the vicinity of kilohertz or lower, in order to do narrow band filtering. It's a lot easier to design filters at kilohertz bandwidth, but you will have to heterodyne all this down to much lower frequencies. You work with lower frequency electronics, and then do all those things. You do have low frequency things at this end, but actually a stepping frequencies down from 42 megahertz. Our signals are coming in from these frequencies, and then it heterodyne down to much lower frequencies. Okay. So at the electronic end, you can see it's low frequencies. But the physics at the very beginning is actually RF frequencies in the tens of megahertz or even hundreds of megahertz range. Okay. Any other questions you have? So Professor Zhupei Liang in our department is supposed to be an expert on this kind of thing. He would work on how to do a fast radon transform and that kind of thing. He will have to, as you can see, all the Fourier data that you have are actually polar in nature. Right? You actually get Fourier data in a polar plot here because of the nature of radon transform. Then they will have to figure out a clever way of doing this transform so that they are n log n. We can interpolate to a rectilinear grid and do an FFT, and then you will have to worry about all kinds of errors that come about. Because some parts are undersampled, some parts are oversampled when you do this image processing. And you have to do clever image processing to get a high resolution image out of that. Okay, you can talk to the professor. Good data. And they also have something called functional MRI. Functional MRI is a hot topic. Is a topic where you can have very high resolution MRI. You can start to do spectroscopic MRI. In other words, these Raman frequencies would be changed depending on where this atom or where this proton is attached to. When they're attached to different parts of a molecule, they will have a slightly different Raman frequency. So they can actually do spectroscopic MRI and study what the Raman frequencies of these protons are. And then by studying the Raman frequencies, they can know where the protons are attached to, what kind of molecules they're attached to. And then they can add trace elements to change the Lamotte frequencies of the MRI. Maybe, I don't know what kind of things they add. Okay. But Professor Zupila would be an expert on this. And then you change the Lamotte frequencies of these protons, you can have different ways of studying the human body. Like if we inject you with something, and then inject you with something, and then put you in the MRI machine. And then before injection and after injection, your MRI image will be different. Okay, so those are called functional MRI. Yes?
Over there, we need a narrow filter to sweep over that frequency range. That's why.
No, you can excite this system with a broadband signal, and the response will also be broadband.
Right. So, but the filter should sweep like a spectrum analyzer does, like sweeping and at any specific frequency with the bandwidth measure.
I don't really know the detail. I know that they have something called a squirrel cage antenna or something for the RF field part. If you look at them, they're pretty complicated in design. They're all like cores. Okay, cores that are designed like squirrel cage. Okay, and then I think they send in a broadband signal. I don't think they send in an RF signal. They just pulse those antennas with the broadband signal and then listen. And then they do signal processing later on. That's my guess. I don't know the detail.
Right. But my question was, when you say it's slow time-wise and you have very narrow bandwidth, are you talking about that you need to sweep per frequency?
Oh, what they can do, actually, to achieve the kind of effect that you're mentioning about, is actually one way is to send out a very narrow band signal, right? Narrow band signal, or send out RF signal that's very narrow band. Or another way is to send in a broadband pulse, but have a repetition of that. Right. This is a repeated broadband pulse. What is the effect of this? The effect of this is to, if you know your Fourier transform well, this is the convolution of this with the impulse train, right? It's convolved with that gap. And if you take this to the Fourier transform space, this is the same as the Fourier transform of this thing multiplied with another cone function, right? This Fourier transform to a cone function. So the end result is that you're actually not getting a broadband signal. You're actually getting a signal like this. This multiplied by this equals that. So one way of getting narrow band signals at prescribed frequency is to have a rep rate. So you often heard about this repetition rate. You have to perform a broadband measurement repetitiously. And they will say, oh, I'm doing this as a rep rate of kilohertz. And you can have this repeating in a kilohertz fashion. And effectively, you're getting this. You're getting a whole bunch of narrow band signals. Okay? So you often hear about rep rates in the time domain broadband measurements. And that is what they meant. You have to keep repeating the measurement. So the stability of if your pulse generator is very important. If this rep rate is not very repetitious, then maybe there's a little bit of shift. That is called the pulse jitter. Okay. So if you want to send in a repeated pulse into the system, you better make sure that this repetition is reproducible. And this is another technology barrier, is that it's very hard to make a pulse generator that repeats exactly 1,000 times by itself. Because every time you repeat, there's a little bit of uncertainty on at which time it repeats itself. That's called a jitter. And the jitter is there, always there. And that actually will not give you this precisely. Mathematically, this give you this give you that give you that. But what happens if this thing is slightly shifted with certain uncertainties because it's outgive? Then you wouldn't have this kind of exact repetition. Okay. So any other questions before we take a coffee break? Okay, you have to hand in your take-home exam today, okay? So we'll take a 5 minute coffee break and come back.